Hello, 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 guys. Hello, hello. Good afternoon already. How's it going? I'm just gonna check that my audio and my video is good. See, I'm just gonna check that my audio and my video is good. Is good. So we're now live. Now, what we're gonna do is continue with the second chapter of developing LLM applications with Langchain, which is something similar to what we were doing in the with the OpenAI array library or the Hugging Face library.
Let's take our LCell chains to the next level with sequential chains. Some problems can only be solved sequentially. Consider a chatbot used to create a travel itinerary. We need to tell the chatbot our destination, receive suggestions on what to see on our trip, and tell the model which activities to select to compile the itinerary. This is a sequential problem, as it requires more than one user input, one to specify the destination, and another to select the activities. Let's code this out. In sequential chains, the output from one chain becomes the input to another. We'll create two prompt templates, one to generate suggestions for activities from the input destination, and another to create an itinerary for one day of activities from the model's top 3 suggestions. We define our model and begin our sequential chain. We start by defining a dictionary that passes our destination prompt template to the LLM and parses the output to a string.
So you create a LLM, you create a destination prompt, and activities prompt.
All using LCell's pipe. This gets assigned to the activities key, which is important, as this is the input variable to the second prompt template. We pipe the first chain into
Okay, the destination prompt result is going to be into activities, and activities is going to be into activities prompt, then
the second prompt template, then into the LLM, and again parse to a string. We also wrap the sequential chain in parentheses so we can split this code across multiple lines. To summarize, the destination prompt is passed the LLM to generate the activity suggestions, and the output is parsed to a string and assigned to activities. This is passed to the second activities prompt, which is passed to the LLM to generate the itinerary, which is parsed as a string. Let's invoke the chain, passing Rome as our input destination. The model considered that we only had one day to explore and wove in its top suggestions of the Colosseum and Vatican City. Time to give this a go.
All right, so learning prompt input variables here. Here's gonna be, I want to learn activity, so the input of this should be the activity. Can you see how can I learn this step by step? Then in the prompt template, we need to define another input variables, but in this case, it's gonna be the learning plan. Here is gonna be the time prompt. Okay. And in this learning prompt, that invoke activity, and here I'm gonna put the time prompt. Try play golf. Okay, so here I'm going to create another one called 6 sequential chains. And in here I'm going to do this. I'm gonna, this is not needed. And then if I run, oh, here from the fused prompting, and here that I did the invoke, I got the result here. The content is here. All right, so here in the 6, if I do Python 6, what it's gonna do is create the prompt with the invocation here. So it's basically gonna just complete this until here. This should work okay. This might take a while. Okay, sequential change with LCL. With your prompt and press creates to tie everything together, including LLM using chains and LCL. An LLM has already been defined for you to use as OpenAI GPT-o model. So first, because I don't have here, I need to put this here. Then this chat OpenAI, it's gonna come from here. And then the LLM is here, so this is good. So this is from the previous example. And then in here, feel free to so at the end I need to put for sure this str out parser so I get the string, and then in the learning plan, which is gonna be the input from here, I should put the time prompt chained with the LLM. This is gonna go as an input, which is gonna be a text in the learning plan, and then in the learning plan is gonna be chained to the the response of this learning prompt with the LLM and the stereo is gonna go to the learning plan, and then here I'm gonna put this, which is gonna receive the learning plan. As an input. And as an input, it's gonna receive, it's gonna be chained with LLM. Then in the sequential chain, I'm gonna invoke, and in this invoke, I'm gonna do this play the harmonica, that is the activity. So first what it's gonna do is like, it's gonna put this into here. It's gonna say, I want to learn how to play the harmonica, can you suggest how can I learn this? And it's gonna return the learning plan, which is here. And then this is gonna be inputted into here. So I will say, I have only 1 week, can you create a conscious plan to help me hit this goal? So it's gonna take the learning plan and it's gonna fit it in 1 week. So this is gonna be the sequential chain. Yeah, I think that's pretty much. So here I do this first with the play golf, and now I'm gonna do everything with the two sequential prompts, and I'm gonna print directly the answer. So I'm just gonna do Python 6, and it should work good. It should also work okay. Yep. Okay, next lecture. There's in Langchain agents.
Now that we're confident with LLMs, it's time to move on to a hot area of AI application development, agents. In Langchain, agents use language models to determine actions. Agents often use tools, which are functions called by the agent to interact with the system. These tools can be high-level utilities to transform inputs, or they can be task-specific. Agents can even use chains and other agents as tools. In this video, we'll discuss a type of agent called React agents. React stands for reasoning and acting, and this is exactly how the agent operates. It prompts the model using a repeated loop of thinking, acting, and observing. If we were to ask a React agent that had access to a weather tool, what is the weather like in Kingston, Jamaica? It would start by thinking about the task and which tool to call that tool using the information, and observe the results from the tool call. To implement agents, we'll be using LangGraph, which is a branch of the Langchain ecosystem specifically for designing agentic systems, or systems including agents. Like Langchain's core library, it is built to provide a unified tool-agnostic syntax. We'll be using the following version in this course. We'll create a React agent that can solve math problems. We'll create a React agent that can solve the following version in this course. We'll create a React agent that can solve math problems, something most LLMs struggle with. We import create React agent from LangGraph and the load tools function. We initialize our LLM and load the LLM math tool using the load tools function. To create the agent, we pass the LLM and tools to create React agent. Just like chains, agents can be executed with the invoke method. Here, we pass the chat model a message to find the square root of 101, which isn't a whole number. Let's see how the agent approaches the problem. There's a lot of metadata in the output, so we've trimmed it for brevity. We can see that executing the agent resulted in a series of messages. The first is our prompt defining the problem. The
So you get the tool message.
second is created by the model to identify the tool to use and to convert our query into mathematical format. The third is the result of the tool call, and the final message is the model's response after observing the tool's answer, which it decided to round to 2 decimal places. If we just want the final response, we can subset the final message and extract its content with the content attribute. Now let's begin implementing agents.
That's awesome. Okay, which of the following statements about agents are correct? Use my language models to make decisions, yes. I just use tools. Okay, I think this is just too good. Time to have a guy that created your own React agent. Recall that React stands for reason and acting. It takes you a lot of built-in Wikipedia tool. So I'm gonna load this Wikipedia. I'm sorry if this is of create a React agent. The LLM and tools to use. And then the agent is gonna be invoke. And then here content, as far as I remember. Alright, and this is gonna be Alright. Then I guess I need to leave this. Wait. I guess I need to leave this. Then I need to please import the missing libraries here. Okay, let's come back to this.
Now that we've created our first agent, let's take a closer look at tools so we can design our own. Tools in Langchain must be formatted in a specific way to be compatible with agents. They must have a name, accessible via the name attribute, a description, which is used by the LLM to determine when to call the tool. In this case, if the LLM interprets the task as being a math problem, it will likely call this tool based on its description. Finally, the return direct parameter indicates whether the agent should stop after invoking this tool, which it won't in this case. Understanding this required format will help us to understand how to create our own tools. Let's say we want to define a Python function to generate a financial report for a company. It takes 3 arguments, the company name, revenue, and expenses, and outputs a string containing the net income. We make the use of this function clear in the doc string, defined using triple quotes. Here's what the report looks like. Let's convert this function into a tool our agent can call. To do this, we import the tool decorator and add it before the function definition. Don't worry if you're not familiar with Python decorators. The at tool modifies the function so it's in the correct format to be used by tool. Like with the built-in tool, we were the correct format to be used by tool. Like with the built-in tool we were looking at, we can now examine the various attributes of our tool. These include its name, which is the function name by default, its description, which is the function's doc string, and return direct, which is set to false by default. We can also print the tool's arguments, which lay out the argument names and expected data types. Let's put our tool into action. We'll again use our React agent, combining the chat LLM with a list of tools to use, containing our new custom tool. We invoke the agent with an input containing the required information. A company name, revenue, and expenses. The response from the agent starts with our input, then determines that the financial report tool should be called, which returns a tool message containing the output from our function, and finally, the output is passed to the LLM, which responds to us. Let's zoom in on this final message. Here's the final output from the LLM. Notice anything? Here's the output from the tool based on the function we defined. Notice that there's slight formatting differences between the two. The LLM received the tool output and put its own slight spin on it, which you may need to watch out for. Now it's your turn. Which you may need to watch out for. Now it's from the LLM. Notice anything? Here's the output from the tool based on the function we defined. Notice that there's slight formatting differences between the two. The LLM received the tool output and put its own slight spin on it, which you may need to watch out for. Now it's your turn.
Got it. Got it. But before doing to the next one, let's run this first, okay? Because I was using Fable. Jesus. I shouldn't have done that. That's bad. Anyway. I misused my Fable grades on this. I forgot to change the model. My let's already create the other one. This is gonna be called function tools. And in here, okay, so legal tools, like that information. You're creating a POC for an application. Fancy name, POC. What is POC? For an application that allows customers to interface with company data using natural language to retrieve information, important customer data. You've been provided with pandas data frame called customers. It contains a small sample of customer data. Your first step in this project is to define a Python function to extract information from this table given customer's name. So in this one, should get the name, and then in here we do the string that receives a string with customer information based on their name, customers, customer name, and in here we have the if it's equal to name. So we get the customers, the row that has name is equals to name, we get the index, and we get the customer info, we return to string, we return it, and then we need to call this by customer name. In this case, it's gonna be called peak performance. Cool. Let's copy this here. Okay, so in the 7, we did this create React agents. This load tools is coming from the Langchain community load tools. And you get the agent invoke response. That's pretty much it. And then here is gonna use the Wikipedia agent that is built-in from the load tool. So if I run 7, no more Langchain community. Langchain community. So I need to install that. All right, and then, well, if we do this, we should have a proper answer. Should be okay. Now creating a custom tool. So we need to add here the decorator tool. And now this is gonna be a tool. Return customer info, print the tool's argument. So it should be args. So here we, in the 8, we do this tool. And then we do this. And then go here, and then in the next one, integrating custom tool with agents. So we have this. So it's basically we need to do the almost the same as before, but in our case we don't need these tools because it's already, we created our own. Then the agent we define after, and the agent we create the agent LLM tools, and the tools is gonna be the, well, it's gonna be an array here, so it's gonna be retrieve customer info, which is going to be this create agent receives an LLM, then the agent invokes this, and then this is gonna be content, and that's pretty much it. But we now we need to do this invoke, and we need to can you please complete this file? Yeah. Integrate document loaders. Okay, first let's finish this by calling both. So here we define how to create our own custom tools. Here how to load tools into the agents. Here create a sequential change, feature prompting. Well, different ways to make similar things. I think the most innovative thing here is the agents here, in which basically the agent analyzes and starts calling the tools depending on what is my prompt. Yeah, let's create a small mock data frame. Okay, let's listen to this.
In this chapter, we'll discuss retrieval augmented generation, or RAG. Pre-trained language models don't have access to external data sources. Their understanding comes purely from their training data. This means that if we require a model to have knowledge that goes beyond its training data, which could be company data or knowledge of more recent world events, we need a way of integrating that data. In RAG, a user query is embedded and used to retrieve the most relevant documents from the database. Then, these documents are added to the model's prompt so that the model has extra context to inform its response. There are three primary steps to RAG development in Langchain. The first is loading the documents into Langchain with document loaders. Next is splitting the documents into chunks. Chunks are units of information that we can index and process individually. The last step is encoding and storing the chunks for retrieval, which could utilize a vector database if that meets the needs of the use case. We'll discuss all of these steps throughout the next chapter, but for now, we'll start with document loaders. Langchain document loaders are classes designed to load and configure documents for integrations with AI systems. Langchain provides document loader classes for common file types such as CSV and PDFs. There are also additional loaders provided by third parties for managing unique document formats, including Amazon S3 files, Jupyter Notebooks, audio transcripts, and many more. In this video, we will practice loading data from three common formats: PDFs, CSVs, and HTML. Langchain has excellent documentation on all of its document loaders, and there's a lot of overlap in syntax, so explore at your leisure. There are a few different types of PDF loaders in Langchain, and there's documentation available online for each. In this video, we'll use the PyPDF loader. We instantiate the PyPDF loader class, passing in the path to the PDF file we're loading. Finally, we'll use the load method to load the document into memory and assign the resulting object to the data variable. We can then check the output to confirm we have loaded it. Note that this document loader requires installation of the PyPDF package as a dependency. When loading CSVs, the syntax is very similar, but instead we use the CSV loader class. We're seeing a pattern forming. Finally, we can load HTML files using the unstructured HTML loader class. We can access the document's contents again with subsetting and extract the document's metadata with the metadata attribute. Time to begin loading documents for RAG.
All right. So here it says PDF document loaders. To begin implementing retrieval augmented generation, you first need to load the documents that the model will access. These documents can come from a variety of sources, and Langchain support documents loaders for many of them. In this exercise, you will use a document loader and load a PDF document containing a paper. RAG versus fine-tuning pipelines, trade-offs, and okay. So in this case, what we need to do is like from Langchain document loaders, we need to import this PDF loader. And then in this PDF loader, we need to import the this, and in the data we do loader, and then in here we do loader.load. Yeah. And here is py-pdf loader. And then here it should be, here I'm gonna do the 9. py-pdf loader. And in here I load this file. I think I don't have access to this file, so it should be okay. So now it should be good. It run the PDF. And then in the next one we do the same, which is going to be 10 CSV loader. PDF loader, CSV loader. From here, well, I don't remember the name. See, I just CSV loader. Then CSV loader, and we load this. And this in this data we do loader.load. So it's basically the same, but that's the lost CSV. Then here we do the unstructured HTML loader. We do this and this data loader that load print data. Okay, and here in the print data, that metadata. So run. This is gonna be the 11 HTML loader. Okay, save this. Now splitting external data for retrieval.
Now that we've loaded documents from different sources, let's learn how to parse the information. Document splitting splits the loaded document into smaller parts, which are also called chunks. Chunking is particularly useful for breaking up long documents that they fit within an LLM's context window. Let's examine the introduction from an academic paper, which is saved as a PDF. One naive splitting option would be to separate the document by line. This would be simple to implement, but because sentences are often split over multiple lines, and because those lines are processed separately, key context might be lost. To counteract lost context during chunk splitting, a chunk overlap is often implemented. We've selected 2 chunks and a chunk overlap shown in green. Having this extra overlap present in both chunks helps retain context. If a model shows signs of losing context and misunderstanding information when answering from external sources, we may need to increase this chunk overlap. There isn't one document splitting strategy that works for all situations. We should experiment with multiple methods and see which one strikes the right balance between retaining context and managing chunk size. We will compare 2 document splitting methods, character text splitter and recursive character text splitter. Optimizing this document splitting is an active area of research, so keep an eye out for new developments. As an example, let's split this quote by Elbert Hubbard, which contains 103 characters, into chunks. We'll compare how the 2 methods perform on this quote with a chunk size of 24 characters and a small chunk overlap of 3. Let's start with character text splitter. This method splits based on the separator first, then evaluates chunk size and chunk overlap to check if it's satisfied. We call character text splitter, passing the separator to split on, along with the chunk size and chunk overlap. Applying the splitter to the quote with the split text method and printing the output, we can see that we have a problem. Each of these chunks contains more characters than our specified chunk size. Character text splitter splits on the separator in an attempt to make chunks smaller than chunk size. But in this case, splitting on the separator was unable to return chunks below our chunk size. Let's take a look at a more robust splitting method. Recursive character text splitter takes a list of separators to split on, and it works through the list from left to right, splitting the document using each separator in turn and seeing if these chunks can be combined while remaining under chunk size. Let's split the quote using the same chunk size and chunk overlap. Notice how the length of each chunk varies. The class split by paragraphs first and found the chunk size was too big. Likewise for sentences. It got to the third separator, splitting words using the space separator, and found that words could be combined into chunks while remaining under the chunk size character limit. However, some of these chunks are too small to contain meaningful context, but this recursive implementation may work better on larger documents. We can also split other file formats like HTML. Recall that we can load HTML using unstructured HTML loader. Defining the splitter is the same, but for splitting documents, we use the split documents method instead of split text to perform the split. Time to practice.
Guess I think I'm gonna take a small break and then we come back. Okay, I'm falling asleep. Sorry.